Alright, so let's vaguely learn about computers, computer architecture, game making, program making, libraries, and pretty much how you recreate the wheel in computers in a very simple way. Okay, now we start at binary. Now what exactly is a computer? Well, a computer is pretty much made up of a CPU, a RAM, some kind of memory, some kind of power supply. So the power supply obviously gives you electricity. The memory is what you save things on for, if that doesn't wipe, like an operating system, a bootloader, programs, files like games or pictures, etc. A CPU is pretty much just a electronic thinger that does math, is one way to think about it. And we have this thing called binary, which is pretty much zeros and ones, which is like I believe it's one is like an electrical signal, zero is like a negative, or it's like a no electrical signal or something. I don't know, something like that. And then it basically makes letters, because you just have codes, special codes for the alphabet. You have special codes for special characters like numbers and these things and whatever, equals, plus, all that stuff. And it's not unique, as in or it's how do I describe this? Basically, you can make these kind of whatever you want. If you were making like a CPU or making like a programming language, you could potentially recreate the wheel. It's not like A is this, God-given letter that absolutely equals this. It's because they wanted it to equal that. It's just simple, because 0001, 00001, whatever. Yeah, just kind of simple. Then you have 1 and then 1 1. It's just kind of a way to count. Alright, so we get through binary, and from binary we get assembly. Yeah, basically. Now this is x86 assembly. Now what does that mean? Well, have you heard of 64-bit and 32-bit and 16-bit and all that stuff? Well, at least this one is showing 32 bits, so we have bits there. Bits is basically data, zeros and ones. I'm pretty sure 8-bit would be 8 zeros and ones, or the potential of 8 zeros or 8 ones or 8 combination, something like that. I'm being honest, I don't know this 100%. But basically you have this thing called assembly, which is just CPU language, CPU programming language. So it's pretty simple. Well, simple and complex, I mean like the things that you type are simple. Here you type db, declare a byte, dw, declare 2 bytes. 1 byte is 8 bits. I'm pretty damn sure that's how it works. Anyway, right, so here we go, MOV. So that's another code, that's an assembly code for specifically the x86 processor, right? And then you have MOV, EAX, and I don't know if you type that in, I think you type that EVX as well. Move the 4 bytes in memory at the address contained in the EVX into EAX, so memory management essentially. So this is like CPU memory management working with, I don't know if it's working with the CPU's internal RAM or if it's working with the actual RAM, something like that. Here we go, registers, move things again. You have all these commands, these super simple commands, which are assembly language commands. From assembly we get things like C, C++, Python. So this is a super low level language, which means it's super low to the electronics. Something like Python is higher level. It's not very based on the electronics. It's much more based on, it's got so much building up. It's like a pyramid. Python's high in the pyramid. C++ is a little bit lower in the pyramid. C is lower again. And whether you like high or low level languages is really going to be up to you. Personally, I would be using C and I might just switch to C because I don't really use objects. I just don't find the the need. Personally, that's just I don't know. That's just how my mind works. It doesn't really. It feels like the object is just a nice way to package and formulate things. So I can't deny I do like inheritance. But anyway, let's go to Sega Saturn motherboard. So I really like the Sega Saturn motherboard. It's just such a nice thing. Here we have another picture of it, except this is more of a symbolic representation. If you want to see what the actual chips look like, just a black chip with like made in China or whatever, probably just look up, Sega Saturn motherboard. It's pretty easy to just look up on search engine. Anyway, this is a gaming console from the 90s. I think it was like 1994 to 1998, which about the Dreamcast came out like what 1997, 1998. Personally, I'm really sad Sega dumped the Dreamcast. I thought it was it was kind of like it had internet access, and that was cool shit. Um, just was such a nice little console, but they dropped it. Anyway, so here we have the cartridge port, the AV out, the battery. I imagine is that like what, like the CMOS battery to handle time. I don't know, something like that. Audio DAC. Here we go. RGB encoder, system control unit, CD drive controller, and here we go. Video processing display. Here we go. Video display processor 1, video display processor 2, Saturn custom sound processor. So these are like CPUs or control processing units for 2 for video, 1 for sound, a Motorola 68 EC 000 CPU, which that would have custom assembly. So they would have assumingly converted the assembly to whatever whatever programming language was using this. And here's the thing, all of these things, here we go, the RAM here, well, this is all RAM, 3 RAM chips, 4 RAM chips, we do 5 RAM chips, are there more? I don't know. And we have a RAM controller, so basically another CPU here. These are the 2 main CPUs. These are just CPUs to control, video and sound. So many fucking CPUs. Here we go, tiny little chips here, hex inverter. I can't even read what the fuck that says. Bus, trans something or other, controller ports, power LED reset button. You kind of get the point. So pretty much CD driver port. Alright, so pretty much the idea of this is that you've got all the electronic components, like resistors and capacitors. We see these are capacitors. These little things here, I don't know what they are. I can't really see. These things, I forget what they're called, but it's basically a magnet with thick wire wrapped around it. So you have and then you have the processors, which look up actually fuck it, I'll just put a picture of what a CPU looks like in here. It's pretty much all of these lines connecting to all of these things, which allows it to do like addition, subtraction, all that bullshit. So you have all these like components, right? They're connected electrically through other microelectronic simpler component. A capacitor is pretty simple compared to a CPU or RAM. So you've got all these components connected, and then you have a programming language, which is where things get more complicated. Now I have a picture here. This is a C4 engine. Personally, I don't use C4, but I love the picture here. It just really just describes everything. So what you would have, this is a gaming engine, right, which was made from a programming language. So you didn't exactly have a game engine for like the Sega Saturn or like the PlayStation 2 or some other console. You might have gaming engine nowadays. There might be like a PlayStation 5 or an Xbox, whatever the fuck they call it nowadays. game engine, but what you usually had were libraries, and libraries are like a collection here of OpenGEX. Wait, no, never mind. Whatever. So libraries are kind of like, it's like a, imagine you have a pre-written program that handles memory management or file management. These are in basically libraries. Each of these things is like a library that's in a game engine, a sound manager, a graphics manager, input manager, network managing, very important, controller, so you can have input output, so input output manager. If you look at things like, so there are a bunch of different, I don't know if you call them frameworks, or I guess you can call them like GUI applications or GUI assistant libraries or package things or something like that. Things like Vulkan, OpenGL, DirectX, what else have we got? I don't know, things like that. They handle, mostly they handle window management. I'm going to show you what window management is. Now this is raylib. Raylib is basically a code game engine. It's a bunch of libraries. Here you see this is C++, by the way. Include raylib.h. It's pretty much including this. I think it's called a header file, which is like made up. It's got a bunch of different libraries, or it calls to libraries or something like that. And as you see here, we've set the size of the screen, right? And we've set the FPS for it, and some other, bullshit like the color of it. So I'm going to run this program, and as you see here, it's using OpenGL as its window thing. So raylib is a code-based game engine that's accessing OpenGL, which is kind of like a bunch of window and visual libraries, or it is a visual library or something like that, to then access C++ code, which is accessing assembly, which is accessing binary, which is accessing the CPU, basically transmuting electricity through an electrical, I don't know, thing or component to create this what we call a window. A window is, you see this, here you got the close, minimize, basic window. Otherwise it'd just be a console application, which is literally just this. That's not quite as fun. So I'm going to close that. Closes that. So a game engine, or one of those text-based things, has a bunch of things like a sound manager, which pretty much just means in the code you can say, I want to play this music in the code. I should have probably brought up my what do you call it, that Python visual novel engine, I forgot what it's called, but that you basically just say like play sound, whatever. So that would have a sound manager DLL that handles audio, the decompression, the streaming. Maybe it has audio effects, or it has a mixer and all that stuff, so you can pretty much make the sound higher or lower. You can add reverb, all that kind of stuff. Maybe that's a pretty advanced, I mean, that's a bunch of different, like, probably packages in that specifically. Playing video, that's another, video pictures. SDL, I kind of like SDL. It's pretty complicated. SDL is another window thinger. So basically in code you would call the SDL, again I think it's called headers, I don't remember, the SDL headers, and then you would write a shitload of code. it's like 300 lines long to get a window. This is raylib simplifies it. That's why this is easy mode. This is easy mode code. But the easier mode code is a gaming engine. Now this is a basic This is just a basic little game that I've put together, and if we take a look at the so here we go, the main, we have a players made up of things, we have walls so we don't run out of the game, we have an enemy spawner, an enemy timer, so that times the spawner in the script. So gaming engines are really fucking easy. You know, people are like, oh, what gaming engine should I use? Is Godot a good enough gaming engine to make a 3D game? Well, you know, yes, it is. Do you want this nice setup of all this lovely stuff here, or do you want this? Do you want, like, this is actually nice as well. Raylib makes it super easy. You know, go use Vulkan if you know, if you want some complexity, but this is so easy. And yes, this is 2D, but I've made 3D games here. Godot, personally, I like Godot more than Unity because I click the exe and it starts in like a second. Unity, I have to install an update or some bullshit, and then I'm waiting for like an hour, and I just can't be bothered. Anyway, basically just spawn in enemies. Here we go. Movement, basic movement. You know, you're telling the game engine, the computer, how do you want to move the picture, which is this little dot here. Anyway, so we have a little happy opening scene. Everyone's happy, and then we click start, and here we go. And we have some enemies spawning, and I haven't quite worked out the collision and the damage and all that, so they're just literally endlessly spawning until we all get we all drown and die from like triangles. But hey, it kind of looks like Toho, except you're the one controlling, you know, the thing. I think that's awesome. I actually have to make this slower, but you know, or maybe I won't. Maybe I'll just, that'd be pretty wild just having it like this. But anyway, oh jeez, yeah, as you see, we really are drowning now. But you see how easy this is? Like, making a game is it's complicated and easy at the same time because we have so much software. Going back to the Sega Saturn, and like the PlayStation 2 is a perfect example. I have no idea how it was so popular because they didn't make a game engine for the PS2. They didn't make a raylib library. They didn't even make an SDL. So you know what you were doing? They didn't make all this processing for networking and graphics and file managing and I don't know, all this junk. They didn't make a map creator like Hammer editor for Source, or you know, there was they had to create their own. They had to look at the architecture and be like, all right, we have 1 megabyte DRAM, 1 megabyte SDRAM, we have 2 CPUs, we have a central control unit, we have you know, 512 KB of audio RAM, a Motorola CPU. Again, you have to potentially, I don't know how it would work if you had to learn the Motorola assembly code, and then you had to learn the assembly code for individual CPUs here, and then you had to learn this assembly code and all this other bullshit. Or if maybe, I mean, I think for Sega Saturn specifically, Sega made libraries. So you would just kind of call up, you'd be like, alright, access CPU 1, access CPU 2. You'd be like, alright, CPU 1, you are handling all of the physics processes, and CPU 2, you're just handling like the weather effects. You're handling maybe, no, CPU 1, I'll put all of the cycles, so the tick cycle. So essentially every second when an enemy, I don't know, attacks you or spawns, or when HP is calculated, when damage is calculated, we put all the big calculations in CPU 1, and then CPU 2 is just telling the audio thing when to load. So the CPU 2 you load through using the library, which is a collection of code which pretty much has all of this. The audio library knows there's 512 KB audio RAM, so it knows how much it can put on RAM. It knows that it's got a sound processing unit. It knows the assembly code, so you don't have to use assembly code. You just say like call audio unit, play rain song, you know, play enemy hit thing, or a hit sound, or anyway. And this CPU2, maybe it's calling up all the video processing units. So again, the library understands how much RAM it's got. It understands it's got 2 processors, that it's got an RGB encoder, that it's got all this bullshit. So you don't have to handle pretty much anything. The same way that I didn't have to handle shit with this. I just like, this is nothing. This is literally nothing. Or with Godot, you just press the play button and it has a screen. You don't need any coding at all. We can make a new game and it just has a screen. You don't need anything. It's so simple. I hope you understand, like, even the Sega Saturn, like, this is a difficult architecture, but it had libraries. The PlayStation 2 didn't have libraries, so you would have to individually look through the architecture, look through how much, like, look through all of the electronical chips that were in here, look through how much RAM there was, all of the CPUs. You had to understand, look at the flow of electricity, so the flow of how this stuff works. So what is handling what first, so then you can pass it to the next thing. You had to fully understand that, and you had to make your own library. You had to tell it, how do you make a window, how do you process sound, how do you do all this. You probably had to spend like 3 months coding your own libraries and your own game engine before you could even do that. So I guess the final thing is more in like general application programming, which there's things, if you look up like Qt, or I think it's like tk something slash something tck, I don't know. There's another one, wxWidgets, there's GTK4. If you look up all of these things, these are, most of them are library based code, application assistant thing. So basically what happens, it's called a framework. So same way raylib handles Windows really easily, it handles, you know, WASD, movement, input, output. I think it handles netcode, I'm not sure. You might have to get something else for raylib net for netcode, I'm not sure. It handles sound, it handles all these things. There are application things, as I said, your GTK4 handles internet-based netcode, so you can make an app or a program and hook it up to the internet. It handles, you see all this, like these buttons here. This was made in some kind of visual program, so, like, you know, Visual Studios, I don't want to use Basic anymore. Actually, apparently they do teach it somewhere. But Visual Studios, your .NET, all these things. Look up programming frameworks, and this is how you make these buttons, all this shit here. Which is what something like a GTK or wxWidgets, you know, or Qt or whatever does. It makes this just for 2D GUI or graphics user interface based applications. So you don't just have a console based application, which is, you can, but GUI is nicer. So, you know, a game is a little bit different because it has much more 3D stuff. And it has sound and all that stuff. Usually a 2D application. This is a 2D application. Godot is a 2D application. You know, all this stuff was made in some kind of GUI editor. Pretty, you know, pretty nifty looking little GUI. And then within this, we can make 3D games. We can make 2D games. You know, it works perfectly fine. Similarly, the web browser. I have like 100 tabs open. I'm not going to show you my web. You know, I'm not going to show you that. But that's all GUI based applications, which again is built up of libraries. It's got a library for the GUI, a library for the networking, a library for the window, the actual window creation, all of this shit. This is how like programming and computers and all this stuff works. Anyway, I went a little bit quick. I hope you still got the idea of all this stuff. Anyway, that's all. So, of course, I hope you liked the video, and feel free to check the links in the description for social, commercial stuff, and have a nice day.